So, in the last class we have seen that for a motion under central orbit we can write r dot equal to 2 by m e minus v r L square by m r square to the power half, which might not be seen easily, but anyway you know this expression, and theta dot equal to m L by m r square. Now, this one we can write this as total derivative of r and t, and from here we can just shift this in order to write 2 by m e, or essentially what we can do is we can instead of writing this full expression, we can just replace it, we can just call it some p of r p being some function, I mean this particular function, and because it has r here and here, so we can just write this as dr by p of r, this integration, and dt integration. Now, performing this integration will give me r as a function of time, right. Now, this integration on the, so this equation for the for what we have for theta dot is theta dot equal to L by m r square. So, this can be rearranged to get integration d theta equal to L dt by m r square. So, once we solve, once we could integrate this part, we can take r as a function of time, and then we can substitute it back in this equation, and then we can get theta as a function of time. So, essentially we get r as a function of time, theta as a function of time, and in principle once we can perform these two integrals, the problem is totally solved. So, we know that we know r and theta of the entire trajectory as a function of time, which essentially it's equivalent of saying that we know the entire trajectory as a function of time. That is the total solution of the problem we are looking for. Now, there is a technical issue. Solving this equation is hard, because or rather integrating this expression in this particular form is hard, because p r, first of all, it is not a very simple looking expression. Secondly, this v r here is, so there is a to the power half here, I think now you can see it, yes, right, it is fine. So, v of r is not a known function. So, we don't know, it might have singularity at some point, it could diverge at very low or very high values of r. So, we do not want to get the, we do not want to perform this integral in a sense that it might not be a very easy task to perform, especially by hand. So, in order to gain insight, we can also try to get solution of the form r as a function of theta. This will be a time independent form of the orbit. Okay. So, this will also give you the orbit, but it does not include the time explicitly. So, that means it will give you the orbit not as a function of time, but it will give you the orbit as a functional form of r as a function of theta. Now, in order to do that, in order to get this solution, we need to get an equation, differential equation, which includes only r and theta, and there is no t dependence. How we can do that? We can do that by start writing, recalling that m r double dot minus r theta dot square is equal to f r. So, this is the standard equation of motion of central force, under the central force f r. Now, if we replace theta dot by this expression, this reduces to r double dot minus r L square by m square r to the power 4 is equal to f r by m, or just simplify a bit, get rid of this one. Okay. So, it will be simply r cubed here. Now, what do? We introduce a new set of new parameter which we call u as 1 by r. So, it is just the inverse of the radial part. So, if this is the case, then r is also 1 over u, r dot is minus 1 by u square du dt. We can do a mathematical manipulation on this and we can write minus 1 by u square du d theta d theta dt, which is theta dot again, and in this particular notation theta dot, which is L by m r square, will be L u square by m, right. So, if we substitute this, r dot will be minus 1 by u square, and this is your theta dot, d theta dt is theta dot, which is L u square by m du d theta, right. So, you see that u cancels out, leaving behind r dot is equal to minus L by m du d theta. This is one relation. We can do this derivative a second time. I am leaving it to you. So, essentially you have to evaluate r double dot also, because this equation has r double dot. So, you have to take another time derivative of this. Just the same, it will be d2. If you take the time derivative of this, you can replace this as d2u d theta 2, and then there is another d theta dt, which is a theta dot, which has to be replaced back once again. Now, if you do that, your final expression, I am just leaving it to you as an exercise. I think you can do that. So, your final expression for r double dot will be minus L square u square by m square. So, minus L square u square by m square d2u d theta 2, that is the expression for r double dot. Now, it is time to do the substitution here. Take that, substitute it here. So, it will be, and also you have to substitute r for u or u for r here. So, this will be minus L square u square by m square d2u d theta 2 minus L square u cubed by m square equal to f r by m. So, immediately we see that we can get rid of, or rather we can get rid of m square from this side. So, multiply this by m square, which will be just multiplying it, or rather it is by m here, m square, multiply it by m square. So, if you take L square u square common with a negative sign and simplify this expression slightly, it will be d2u d theta 2 plus u equal to, so this will be m f L square u square, okay, minus f. So, this will be f of u, f u by f u by u square m by square. Okay. So, your f L square, yeah, right. So, it is, sorry, this does not look nice, yeah. So, it is d2u d theta 2 plus u equal to minus f u by u square m by L square. Now, in this equation we can solve this equation to get u as a function of theta, which is equivalent of getting r as a function of theta, right. So, because we already know that u and r, they are just related by u equal to 1 by r, right. So, this is the equation we will be using mostly for our description of getting a description of central orbit, or sometime we will be using it to find out law of force, sometime we will be using it to get the differential equation when we know the law of force. We will take up these examples very soon and we will see. Now, before going there, we can also get an alternative equation which is not a homogeneous equation, but that is a first order equation. If you recall, the energy expression was E equal to kinetic energy plus potential energy. So, if you do that, you will simply get half m r dot square plus L square by 2 m r square plus V of r, right. So, if we now substitute r dot with this expression and r with u, then energy expression becomes half m L square by m square du d theta whole square plus L square u square by twice m plus V of u, right. Now, rearrangement of this gives you, so you see 1 m cancels immediately and we can take L square by 2 m common, right. So, if we take L square by 2 m common, we have du d theta whole square. So, I am just writing a new step here, u square is equal to E minus V of u, or sorry, not this, du d theta whole square plus u square equal to 2 m by L square E minus V of u. So, this is another equation which is not exactly, so this is a second order homogeneous differential equation, this is a first order inhomogeneous differential equation, because we have a du dt whole square, but this is also usable at some point, this is also useful for certain cases, we will see that soon. Now, before moving into any further in the by using this equation and see what happens for different cases, let us take some examples. Okay. So, we have some classroom problems like we have in our every class. So, the first problem is a particle moves along a spiral described by the equation theta dot equal to omega equal to constant, r equal to r0 e to the power beta t. We have to find an expression for the acceleration a. So, what is given? It is given that theta dot is equal to omega, which is equal to a constant, r equal to r0 e to the power beta t, right. Beta t. So, if this is r0, r dot will be r0 e to the power beta t times beta, r double dot will be beta square r0 e to the power beta t, right. Similarly, theta dot is equal to omega equal to constant, theta double dot is equal to omega dot equal to 0. So, the expression for A, in order to write an expression for A, we have to keep in mind that it has both radial and transverse component. So, we have A is equal to r double dot minus r theta dot square r cap plus 2 r dot theta dot r theta double dot theta cap, right. Now, r double dot, right. So, if we perform this first, if we expand this first part and put values from, sorry, no, not expand, if we just put values here, so we get, so this is essentially beta square r, okay. So, we get r out have beta square minus omega square r cap plus, now theta double dot is equal to 0. So, this term does not contribute to our final expression. R dot is r 0 e to the power beta t times b, beta which is essentially beta times r. So, we have 2 beta, or I will just write it down for clarity, plus 2 beta r into omega theta dot, right. So, it is all final. We will just rearrange the second term, bring the constants omega r theta dot. So, we have this as our answer. So, we have r times beta square minus omega square equal r cap plus 2 beta omega r theta cap. So, this is the final expression for the acceleration A in this particular case. Good. Now, let us move to the second problem, which says find the parametric equation r equal to minus a t, theta equal to minus b by t, where a and b are constant. Prove that the parametric equation represents a central orbit, and also you have to find the force law, right. Now, in order to find out whether if it is a central orbit, what do we need to do? Let us come to the board again. So, we have to first prove, now what is a central orbit? Central orbit means r square theta dot will be equal to 0. So, if we can prove that for this particular set of parametric equation, which is r equal to minus a t, theta equal to minus b by t, we can prove that r square theta dot is equal to 0, then that essentially proves that this particular set of parametric equation represents a central orbit. Now, theta is equal to minus b by t. So, theta dot is equal to b by t square, t being a time. So, in this case we can think of t as the time, right. So, this is the parameter, time is the parameter in this parametric equation. So, essentially the equation of the orbit is given in terms of the terms of the parametric equations. All we need to do is we need to eliminate. So, in order to, okay, we will come to that later, fine. So, we first estimate theta dot. So, r square theta dot will be nothing but minus a t s, sorry, minus will not be there, a square t square into b by t square, which will be a b. So, r square theta dot is equal to a b equal to a constant. Okay. So, that is our equation. So, we essentially proved that this orbit represented by this particular set of parametric equation is a central orbit. Now, the second part is we have to find out, right. Now, we have to find out the equation of the orbit. I am leaving it on you, because what you need, all you need to do is we need to eliminate r and theta, I mean sorry, from the expression of r and theta you need to eliminate t. So, essentially you have to get r as a function of theta. You can do that. Okay. So, I leave it to you and we move to the next problem. So, next problem is also related to the first problem, which says for the particle of that for the particle's trajectory given in problem 1, which is the first problem here, the spiral. Okay. Set beta equal to omega and find the law of force. Okay. Now, this is once again this is also easy. What happens is, if we set beta equal to omega in this equation, if you recall, right, r is equal to r 0 e to the power beta t. Now, it will be r 0 e to the power omega t, and theta dot is equal to omega equal to a constant. Now, if we integrate this equation, we get theta minus theta 0 is equal to omega t. Okay. So, we substitute this for omega t and we immediately see this equation becomes theta minus theta 0. Okay. So, this is the equation of the trajectory. Right. So, in case when theta is equal to omega, this is the equation of the trajectory. So, we get r as a function of theta. Now, what we need to do is we need to find out the law of force, which is f of r. Now, recall that d2u d theta 2 plus u equal to minus L, I always forget this expression, m by L square u square f of u. So, what we need to do is we have r as a function of theta. So, we have to construct u first, then we have to determine d2u d theta 2, substitute it here, and we will essentially get an expression for u f of u in terms of theta. Now, if r is equal to this, so u will be equal to 1 by r 0 e to the power minus theta 0. So, du d theta is equal to minus 1 by r 0 e to the power minus theta 0, d2u d theta 2 is equal to 1 by r 0 to the power minus theta 0, which is equal to u. So, we see that du d theta d2u d theta 2 is essentially equal to u, and this is equal to minus u, which is not very uncommon for exponential functions. On subsequent derivatives, they sometimes repeat themselves, sometimes repeat them with a negative sign. This is exactly what is happening here. So, this part is nothing but 2u, and the right hand side we have m by L square u square f of u. You have to bring this u square to this side, and rearrangement will tell you that f of u is equal to minus L square by m. So, there will be a 2 here, it will be u cubed, we are writing 1 by r cubed. So, this is the final answer. So, we get a force law which is attractive because there is a minus sign, and which is proportional to the inverse of, or rather 1 over r cubed. So, the force which gives this type of a trajectory is a inverse cube force, attractive. So, just for your curiosity, the particular type of spiral which is described in this problem, when beta is equal to omega, this particular spiral is called a logarithmic spiral, and this is a very interesting trajectory. We probably will come back to it and do some more problems. Now, let us move to the fourth problem. Fourth problem is a particle of mass m moves under the influence of central force given by this. So, this is a repulsive central force because there is no negative sign and we have r to the power 5 dependence. We have to set up the differential equation of this particular orbit, and the differential equation is the same, d theta 2 plus u equal to minus m du d theta. Now, what is given is the force law. So, this side is given f of r is equal to 2 L square r capped by m square r to the power 5, m square r to the power 5, right. So, f of u, so we just have to replace r with 1 over u and we immediately see that this gives you to the power 5 m square. When we replace it back here for fu, we get 2 L to the power 5, sorry L square, sorry, by m square, L square gets cancelled out, u square is here, so we get u cubed and also we can get rid of 1 m here. So, essentially the differential equation becomes minus 2 by m u cubed, minus 2 by m u cubed. So, this is our answer. So, all the problems what we have described here, these are very simple problems. In reality, sometime we have to solve this differential equation. We will take up some more examples as we progress, as we go on in our classes. But right now, I just wanted to show you how to use this particular form of differential equation or particular form of expression what we have got for connecting u and theta. In order to, first we showed how to solve this equation to get the equation of an orbit, and secondly we took a force law and showed you how to set up the equation of motion. Now, how to solve this equation, that is a different question altogether, but of course, I took easier examples in order to demonstrate it easily in this classroom. We will have little more complicated problems next class onwards. Also, what we are going to do is in the next class, we need to, so again recall that the original equation has a particular form which is m L square u square. Sorry, I always forget this particular form and I have to look back to my notes. I hope you will excuse me. So, what we will do is we will try to solve this equation for a very particular type of force which is k u square. So, k u square essentially means f r is equal to k by r square. There could be a negative sign for attraction, there could be a positive sign for repulsion. But this force law is extremely familiar to all of us. This is the inverse square force field which consists of gravitational force, which consists of electrostatic attraction or repulsion. So, this is a very common force which is seen universally in the world we live. So, we will take this up in the next class and see what type of particular do we get any very specific information about the orbit by putting this value in this particular equation.